This is my practice talk for the Berkeley Arithmetic Geometry Seminar. Let's see. All right. So this talk is about my mic's on. About the Witfinitesimal. Let me make sure that this is bright enough too. Okay, so the Witfinitesimal Torelli problem. Okay, so the main takeaways here, so the main points are that so-called Deligne-Illusie classes so these things behave like Kodaira-Spencer. Okay, and then and the other thing that I want to say is that the vanishing of Deligne-Illusie classes of Deligne-Illusie detects complex multiplication. Okay, all right. All right. So to start the story, we need to talk about the main object of the construction, and so these are p derivations. So I will have talked about them already in the pre-talk, right? But okay, so in this talk, so we're gonna so let B be in the category of commutative rings over A. So this is the category of A algebras. Okay, then a map delta from A to B such that we have the following. So here we have A. So we'll go A. So to the Witt vectors of length 2. Okay, and so the map's going to go A to A delta of A. So this makes sense because B is an A algebra. And so I just want you to recall that this thing here is, well, as you can already see, this is B cross B as sets. And then it has this wacky addition and multiplication coming from the Witt vector rules. Okay, so such that this diagram, so we have this, here's the algebra map. This is the algebra map. Okay, such that this commutes, and this is this map here is the projection onto the first component, such that this diagram commutes, such that this thing commutes is called a p derivation. All right, let me turn off my Teams. Okay. Okay, so this is a definition. Okay, so so these will be called. So do I need any notation? So maybe the set of p derivations be denoted by p derivations from A to B. Okay, so this is a little notational thing. Oh. Okay. So there's a bunch of standard examples, but basically, so there's the Fermat quotient operator, which is x minus x to the p divided by p on the integers. That's a p derivation. So whenever you have a p derivation, so anytime you have a lift of the Frobenius and you subtract x to the p and then you divide by p, that's a p derivation. And every p derivation gives you a lift of the Frobenius. And what else do I want to say? And another way to say this is that a p derivation is satisfies some sum rules and some product rules, right? And yeah, they satisfy some rules and product rules, and that's all I want to say about that. So okay, so derivations of the Frobenius. So the other thing is that we're going to have derivations of the Frobenius are going to be involved. Okay, so okay, so a derivation of the Frobenius. A derivation of the Frobenius is a map. Well, here D from A to B, where B, where B is an A algebra, and the characteristic of B is equal to P, prime P, such that, so I probably should have put that at the top, such that they have the Leibniz rule, such that it's linear, right? And then it needs to satisfy, so this is dA, b bar to the p, plus a bar to the p, dB. Okay, and so we're showing that this is the image in A. So here it's a characteristic p thing. So notation. Okay, so if for schemes, okay, so we will be typically working schemes over a ring R, which is an extension of ZP, but it's contained in OCP, okay, and what else are we going to have? So let's say flat over a ring R, and what else are we going to do? So let's do this. Let's do it like this. So if X is a scheme, so let's do this. So we're going to let R be a complete discrete valuation ring with residue field field K. And this is going to be characteristic P. So let's say it's contained in FP bar. And then we're going to do, we're going to let, so what else are we going to do? Okay, so if X is a scheme over R, and let's say flat, then we're going to, well, let's just take a scheme over R. Then X to the n is going to be, so let's do R to the n is R mod pi to the n. So this is the uniformizer, and X to the n is going to be X tensor with R over Rn. So the reduction mod n, in particular, pi to the n plus 1. In particular, so x0 is going to be x mod pi. Let's do x mod p. Let's just do p's here. Let's make things even easier. Okay, so let's do this notation. So notation. So if x, the sheaf of Frobenius derivations will be denoted by here. Okay, so further, so notation for notation. Okay, so typically we work over ZP unramified completed. This is FP bar. And so we'll call this R. I guess we should just do the whole thing. Okay, let's do this. Okay, so then, so if X is a scheme over R, then Xn will be X tensor over Rn, a scheme or formal scheme. Then X0, well, that'll be where Rn is R mod p to the n plus 1. Okay. And so this is actually the pullback of the Frobenius tangent sheaf by the absolute Frobenius. Okay, so in some places we're going to need to work with ramified extensions, and instead of a pi, we might have a pi to the n plus 1. In some places we're going to need pi derivations as well, and then sometimes we'll need the Q Frobenius here. But that will, I'll mention that when we need this. Okay, so Deligne-Illusie classes. Or formal scheme, let's say. Okay, so P formal. Okay, so we're going to p-adically complete everywhere. Okay, so Deligne-Illusie classes. So let's let X be a smooth P formal scheme over R. Okay, so this is, and let's say for simplicity, it's ZP unramified completed, but you can do other things. Okay, and so what we'll do is I'm going to make the construction right now. So we're going to let UI to X for I and I be a cover by affine opens. Okay, and then what we're going to do is we're going to take delta I. Here, this is going to be a p derivation on UI. By that I mean it's on O of UI. So it's a p derivation from it to itself. Okay, so then what we can do is we can define delta ij is going to be defined to be equal to delta I minus delta j mod p. Okay, and so this defines this is the map where you plug an element in, you take the two p derivations, you subtract them, and then you reduce mod p. Okay, so this thing is an element of the Frobenius tangent sheaf of its reduction, okay, of t of x0 of uij, where, of course, this thing here, where uij is ui intersect uj as usual. Okay, then this gives us a check cohomology class here, which is an element of h1 of x0 with coefficients in the Frobenius tangent bundle. Okay, so this thing here. This is the Deligne-Illusie class of so it's an invariant. It only depends on x1. So I'm just going to denote it by di of x1 here. Okay, so this is by definition the Deligne-Illusie class. So this appears in the definition of the derived Cartier operator in the actual paper of Deligne-Illusie. So that's why it's named this way. Okay. So so because of the way that p derivations and derivation in lifts of the Frobenius are related, so that every time you have a p derivation, you have a lift of the Frobenius. So this Deligne-Illusie class is an obstruction to the lift of the Frobenius mod p squared. So note, so lemma or remark, theorem, I don't know, remark. So di is an obstruction to a lift of the Frobenius modulo p squared. Okay, so there are other, so let me make a second remark. So if you replace, so replace p derivations with pi derivations. So for pi, a uniformizer in some ramified extension, and replacing p with q, which is some power of p. Okay, so this gives us some class here, di, I don't know, we could call it m of x1. So this is an obstruction to a lift of the Q power Frobenius. Okay, so there's variants of this construction that I'll make use of. So p to the m, let's call it like that. Okay, so there's versions of this that you can do for the Q power construction. Okay. All right. So all right. So okay. So we talked about the Deligne-Illusie classes, and I want to compare them to Kodaira-Spencer classes. So for Kodaira-Spencer classes, okay. So what we're going to do is we're going to take, so here we're going to do X, a smooth scheme, over K. And so this is a field with a derivation. Okay, and let's say it's characteristic 0. Okay, and so what we're going to do, and we'll also suppose that it's algebraically closed. Okay. So in the Kodaira-Spencer construction, right, so you do the same thing. Okay, so you'll get the Kodaira-Spencer class of this thing. So I guess this is associated to X is equal to the this is equal to the difference between lifts of the derivations on open sets. Okay, and this is in H1 of X P of X over K. Okay. So, so this is the Kodaira-Spencer class. All right. So one thing I want to note is that so here these DIs. So these are prolongations of delta, i.e. that means that delta I restricted to K is just delta. Okay. And note that, that this means that this thing here, this is K linear. All right. Oh. Okay, so this is the version of the Kodaira-Spencer that we're going to do. It's kind of like the family. So we're only kind of using the generic fiber version of this. And I talked about that before. Okay. So okay, so there's a couple ways in which these two constructions are analogous. Okay. So analogy 1. Okay, so this is going to be the Kodaira-Spencer. All right. All right. So so this class here okay is the class to the first jet space. So we have this thing here. So there's a torsor. Okay, so this is the first jet space. And so here, so this represents, so this thing represents prolongations. And as we saw, it's a torsor under the k linear derivations. Okay. Okay, on the other hand, we have Deligne-Illusie classes. Okay, so this thing here so it only depends on x1 is a class to the Boolean's first jet space here. So JP of x0 to x0, so mod p. So mod p. So this is the Boolean or Greenberg transform, and so this represents p derivations mod p. Okay, and it's a torsor. So it's a torsor under the Frobenius tangent bundle. Okay, so that's the first analogy. Okay, analogy 2. Okay, so we're going to do this again. So analogy 2 is descent. Okay, so there's a theorem. So this is due to Boolean, but the analytic version is due to Erisman. I think there's 2 n's. Okay, so here in this we suppose that x over k is proper. Okay, and then k needs to be algebraically closed. Okay, and so in this situation, the following are equivalent. So 1, the Kodaira-Spencer class is 0. 2, so x over k admits a global prolongation. Okay, so we know those two from just torsor theory. And then 3 is that x is isomorphic to x0, so it's some base change of something defined over the constants. So where x0 is a scheme over k delta, and this thing, k partial, is the set of a and k where delta a is equal to 0. So again, so this is always in a differential algebra setup. So what it says is that this detects whether or not it descends to the constants. So this is the isotriviality condition. Okay. So, I mean, I guess Eris, I don't know who else to attribute this to. But in the differential algebraic setting, it's due to Boolean. Okay, so these aren't really exactly like the Kodaira-Spencer classes because of because we're only working with a field under a derivation. And note that this K can be really, really wild, right? It could be, it doesn't necessarily need to be the generic fiber of a scheme. It could be some crazy meromorphic functions thing, okay? So it could be like the generic fiber of some family over, you know, some analytic space. And those spaces appear in like Joanna Liu's book on Pfaffian differential equations. Okay, so so in the Deligne-Illusie case, right? So this is the Kodaira-Spencer side. This is the Deligne-Illusie side. Okay, so here we have that di x1 is 0 if and only if x1 admits a lift of the Frobenius and this is if and only if x1 admits a lambda p structure in the sense of Borger. Okay, so this is some sort of descent to the field with one element, is the way we think about it. And I'm sure I offended people by saying that. Okay. So analogy 3. So we have Kodaira-Spencer. And so we have Deligne-Illusie. Okay. So if F so if this is a morphism, so if is a morphism of K schemes, then we have that so here, this thing, so if we push forward and then we pull back one, okay, so we have this compatibility condition. So this is, I guess, a theorem as elements of H1 x f star t of y over k. Okay, so this is a theorem. Okay, so this is this compatibility condition for these guys, and so so there's another theorem. There's a similar compatibility condition here. Okay, and it says that if f x to y is a morphism of R schemes, then let's say R is ZP unramified completed, or one of those extensions, then df star so is equal to of the Deligne-Illusie class of x1 is the pullback of the Deligne-Illusie class of y1 inside as elements of so h1 x0, then we pull back, I guess, with the reduction mod p of f star of t of y0. Okay, so I guess I could put a y0 there if we want. Okay, so there is this. This is the key compatibility. So compatibility. All right. So there's two proofs. So there's two proofs of this. So there is so there's kind of a hands-on proof. So this is a geometric kind of hands-on proof. So this is by myself and Zurich Brown. And then there is the kind of a derived category proof. And / cotangent complex proof. Okay, and this is Zdanowicz, who's a student of Piotr Oettinger. And then there's a three-author paper plus Zek. Okay, so so there's two proofs. So this one goes through properties of the jet space, right? And then this one, in this one, it really goes back to this thing here. They define they define deformation tuples, and I think they define deformations of deformation tuples, and then using, and they use formal properties of these. Do I want to say formal properties? So they use properties of these deformation tuples. So they go through kind of just like a laundry list of ways that these things could behave under certain diagrams, and they get it in a derived sense. So and this is why because of this one, we don't need to include the proof of we don't need to include the smoothness assumption here. Okay. And so this paper is in Bordeaux. And I'm not sure where the other paper is. Okay. So we have those compatibility conditions. And now I want to talk about the Coleman conjecture in complex multiplication. Okay? So in the applications. I should say potential applications. Okay, so let me just kind of say some history of this. So a little bit of history. Okay, and so I really have the setup of the problem, but I can't. I don't have a proof of things, but how do I want to say this? So let me just say some history. Okay, so Boolean in the 90s. So this is was able to define. So it had a finer invariant than just the Kodaira-Spencer map vanishing, right? So he defined what's called the Kodaira-Spencer rank. I think he just called it the delta rank, and it's the rank of the Kodaira-Spencer if you view it as a map under where if you view it as a certain map. I'm just going to leave it at that. Okay. He defined the Kodaira-Spencer rank, and when it was rank 0, meant that the Kodaira-Spencer rank being 0, this implied vanishing. Okay, so and what he was able to show was that there's so he was able to show. So he constructed differential algebraic here. So these WR. So this is a subset of the moduli space of principally polarized abelian varieties with level structure here. So this is a differential algebraic set, so differential equations, right? So this is equal to the set of abelian varieties with Kodaira-Spencer rank less than or equal to R. Okay, and then so this is the first thing he showed. One, he showed this, and then the second thing he showed was so there's two things. He did one thing, and then the second thing he did was he showed that these are delta closed. So these are closed in the Colchin topology. And then, this is one of many results in this series of papers. So the series of papers is geometry of differential polynomial functions 1. Okay, and then he showed that the Torelli locus was not contained inside W G minus 1. So this is the ones that were of rank G minus 1. So in particular, generically, differential on a differential algebraic open, we have that the rank, the Kodaira-Spencer rank is maximal. Okay, and so we'd be interested in doing this for doing something like this, and this will be similar. So if you could do this, you would have something like the Dwork-Ogus theorem. Okay, so let me say that. Okay, so let's talk about complex multiplication. Okay, so definition. So I guess I don't need to say what a CM field is. Do I need to say what a complex multiplication is? Maybe not. Okay. I guess I do, because I need to say sufficiently many complex multiplications, and it really matters. Okay, so let me just do this quickly. Maybe I'll just flash this one. So a CM field is a number field, F over F0, another number field, where F0 is totally real, F is totally imaginary, and this degree here is 2. All right. So let me just say definition. So a CM algebra is a product of CM fields. Okay. So so now we need to define what a complex multiplication is. So let A over R be an abelian scheme. So let's say the dimension, the relative dimension is G. Okay, so a complex multiplication is a map J from F to the endomorphism ring of A over R, like so, where F is a CM field. Is a CM field. 2, so we say that A has sufficiently many complex multiplications if and only if. So there exists some P inside the endomorphism ring, A over R over Q, semi-simple, and the dimension QP is 2G. Okay, so so abbreviation. So let me just make an abbreviation. Okay, we say S or A has sufficiently many complex multiplications if 2. Okay. So there's maybe some remarks are in order. So some remarks is that if just a quick remark. So 2 implies P is a CM algebra. Okay. Okay, so let's do a conjecture. So let me just talk about the Coleman conjecture. Okay, so let's do the conjecture. Okay, so if G is greater than or equal to 8, then there are finitely many curves isomorphism classes of curves X over the complex numbers such that A is the Jacobian of X has sufficiently many complex multiplications. Okay, so let me make some remarks. So one is that Coleman conjectured original conjecture was for G bigger than or equal to 4. But Nut and de Jong found a counterexample. Okay, and these are for superelliptic curves. And then they said something like this is a reasonable expectation because their counterexamples don't exist. Maybe there's more, I don't know, but their procedure won't work. Okay, and the other remark is that there's no hyperelliptic hypothesis. Okay, so there's this conjecture. We have the stuff about lifts of Frobenius, and now I'm going to put it together. Okay, so what is the Witt-finitesimal Torelli problem? Well, okay, so Witt-finitesimal Torelli. Okay, so let's let x over r be a curve. Okay, and let's let a be the Jacobian of x. And so let's let j here from x to a be the Abel-Jacobi map. Okay. So then the Witt-finitesimal Torelli map Okay, so this is the Witt-finitesimal Torelli map. It is the map dj star from h1 of x0, f star of the tangent bundle of x0 to h1 of a0, tangent bundle of a0. Okay, and it has the property that, so the key property is that the Deligne-Illusie class, just like the Kodaira-Spencer class gets maps, so it maps the Deligne-Illusie class here to the Deligne-Illusie class here. Okay, and so so the problem, so the question is, so the Witt-finitesimal Torelli problem okay, is that so it's determined the set of x1 such that dj star of di x1 is not equal to 0. Okay, so let me just so let's just recall what happens in the differential algebraic case. So by comparison, with the differential algebraic case. Okay, so we have this Torelli map. So we have the infinitesimal Torelli map. So we have this map here from h1 x to x over k into so some thing here of h1 of a t x over k. So this thing here is, so this is dj star. This is the infinitesimal Torelli map, and this thing here is isomorphic to the second symmetric power of h1 of a OA. Okay. So so this is the infinitesimal Torelli map. Okay. And the point here is that, well, so that's the case. So so I guess you have to take duals and show search activity. So I guess this is isomorphic to this thing dual or something. Okay. So so the Torelli theorem. Okay, so the infinitesimal Torelli theorem it says that so the map dj star is injective outside the hyperelliptic locus. Okay, and to relate this to so there's kind of a little bit going on here in that this is still true, but you need to work, well, I don't know how to say this. Well, I guess I'll just wait for someone to try and catch me. Okay, so so this is injective outside the hyperelliptic locus, and so like an upshot of this is that if if x does not descend to the constants, right, then this implies that the Jacobian of x does not descend. Okay, and actually, the ones that do descend that can be cut out by a differential algebraic variety. There's actually something finer. There's a finer invariant than that. Okay, so all right. So back to the. Okay, so let's go back to our the Witt differential case. Okay, so so there's a theorem that's of Raynaud, and then I have a paper on this topic in higher dimensions that says that, and then Piotr and collaborators have a paper that does things that are more general than this. Again, so it says that so you can also look at this Oettinger, Zdanowicz. So they have a complete characterization of when you have lifted Frobenius. But okay, so these are kind of like beefier versions of this. But if x over r is a smooth projective curve, and the genus of x is bigger than or equal to 2, then this implies that the Deligne-Illusie class here is not equal to 0. Okay, so as a consequence, so note that if dj star were injective, then this would imply then this thing here if this was the Jacobian of x. Okay, so it would not have a lift of the Frobenius. And then okay, so this is true. I mean, this is true, but this is not. It's way too much to ask. Okay, so lemma. The map is not injective. In general, I mean, this is an easy computation. Maybe you guys have already did it, But okay, so by Riemann-Roch. So by Roch here, H1 this thing. So this is 2p plus 1, g minus 1. And also in another computation. So we have h1 of a0. So if we made this as big as we want, then whenever, so this implies if we have 2p plus 1, g minus 1 is bigger than g squared, the map can't be injective. Can't be injective. Okay. Okay, so also note we also know of Jacobians with complex multiple. So we also know of Jacobians with lifts of the Frobenius. Okay, so in the positive results direction, right? Okay, so there's a result of so there's a theorem of Dwork and Ogus plus Ogus, and then there's the same result was proved by Sakaguchi and Ort. It says that so outside a closed subset of you're going to take the A G1, and we're going to take the ordinary locus, and so it has to be reduced mod p, and then you take the ordinary locus, I guess. So the ordinary should be out here. Jacobians do not have a lift of the Frobenius. Okay. Okay, so now I'm going to spend the remainder of the time explaining how Frobenius lifts in SMCM are related. So how are so there's this relations between so the relationship between Frobenius lifts and complex multiplication. Okay, so this is going to be a little bit of Serotape theory. So the theorem is as follows. So let R contain ZP unramified completed be a finite extension. So with residue field, so I guess this is implied, but with residue field, K, which is FP bar. Okay? And so let A over R be an abelian scheme. So A is quasi-canonical. Implies A has sufficiently many complex multiplications. Okay, so this is the first part. The second part is the second part is the following. It says that if A over R is an abelian scheme, and R is a finite extension, of ZP, then if A has sufficiently many complex multiplications, implies A is a quasi-canonical lift. Okay. Okay, so to do this, we need to do some Serotape theory.